All right. Thank you very much for the organizers for inviting me to this Moonshot project. This Moonshot project is really in line with like what I'm very much interested in, and it's been great to hear the presentation so far. I'm at Duke University, which is in North Carolina, and I also just want to disclose that I'm an advisor for the company IonQ. So, as we all know, we have basically one problem, which is that current quantum computers are too small and too noisy. And we'd like to do things with them. So my background is in chemistry, so I'm very motivated by also the Moonshot goals of simulating these large molecules and understanding how they work. I would like to break Bitcoin, just so I could, I guess, steal all the wallets, but also so my students will quit talking about it in class. And then, of course, there are these physics models which seem a little bit closer. When we look at the cost of doing these problems, so let's take one of these chemistry algorithms. It ends up taking many, many operations, more than 1 billion operations, which is not surprising when you think about how many operations are available on large supercomputers. And early estimates suggested that you would need even more, but there's been a lot of improvements theoretically, and I'm part of a National Science Foundation Quantum Leap Challenge Institute for robust quantum simulation, which is trying to further figure out how to make these things simpler. So one thing you could think is, well, I will just get rid of all of the technical noise in my lab and do quantum control. And people have different arguments about where this is going to get to, but it's not, my own opinion is it's not going to make it to a part per billion. So we can improve these algorithms, but there's sort of two challenges. The first is we might improve them too much, and then we don't need a quantum computer. That's actually good for the world, so that's fine. But oftentimes we can trade off the number of qubits for the number of operations. So the goal that the whole community is following is how can we scale up this hardware to, again, millions of qubits, as we heard in the last talk, and then transform those millions of qubits into hundreds of qubits so that we're able to do our problem. Now, when we talk about scalability, there's kind of two arguments. So there's an atomic, molecular, and optical physics argument which says qubits given to us by nature are the most scalable because all of them are the same. But of course, there are challenges in control and confining large numbers of these qubits. And then there's sort of a human-crafted qubit argument, which says every qubit's the same up to manufacturing defects, but we can print basically as many as we want onto a chip. And this isn't just an example of some exchange-coupled qubits from HRL. My point is that Hilbert space itself is very vast. There are very few systems that are really two-level systems. We choose a qubit out of a vast range of choices. So just as an example, this is like one of my favorite examples, is if you read this very nice review paper from 2010 about different technologies for superconducting qubits, what's interesting is these 3 qubits are highlighted. The transmon has already been invented, but it doesn't make the figure. It's not good enough yet to make the figure. So now when you go to this more recent review article from Will Oliver's group at MIT, all of the figures are transmons and kind of fluxonium, but kind of like modifications of transmon from my non-superconducting point of view. Same is actually true with ions. So with ions and atoms, we have less choices, right? Nature gives us some energy level structure, but people choose very different ways to represent the qubits, either in the ground state or through these metastable states or these optical qubits. Yeah, there's plenty of choices. So what quantum error correction does is it basically makes the Hilbert space way bigger. So now what I'm going to do is I'm going to bring together a large number of quantum bits, and I'm going to pick some subspace of this massive Hilbert space, which is my code. Now, how do I pick this subspace? I pick the subspace so that the errors that I expect map me to an orthogonal subspace. And that mapping allows me to detect that I've moved, that I'm in some other spot. And then I can do correction if I can map back. Yeah, so as Professor Fuji pointed out, there are many examples lately of error correcting codes, starting in sort of maybe 2015, 16, a real burst of activity in the last couple of years, because the complexity of our quantum devices has become sufficient enough to actually implement these things. I'm going to talk about this work I did with Chris Monroe, which is the top block with Bacon Shore. Somebody brought up, Professor Pfister brought up these GKP type codes, which I think are a really interesting base code for a concatenation procedure. I think what's interesting is the Honeywell Quantinuum effort has now been able to do logical qubits between codes, which is quite nice. And that's why I want to just bring up the next question about tasks. So my friends who work on human-based qubits are often worried about memory because their fundamental error is T1, T2, which depends on fabrication. Those of us working with atoms and photons and ions, memory is not our problem. Our problem is gates. So our goal for what we'd like to get out of an error-corrected procedure is something different. So I will work through an example. I'm really thankful for Professor Fuji for providing such a nice introduction. So let's just pick one code, a stabilizer code. So the stabilizer code takes n qubits, physical qubits, encodes k logical qubits, and has a distance of d. So it's basically the +1 subspace of n minus k commuting Pauli operators. Surface code is very nice because we can write these symmetry operators as local checks. Here they're represented as red and blue for x-type checks and z-type checks. And we can just write this nice 2D representation. So the z-type checks find x-type errors because z and x don't commute. X-type checks find z-type errors because x and z don't commute individually. These stabilizers commute because the overlap is 2 x's or 2 z's. So in the surface code, the way we do decoding, for example, is if these 2 z-type checks, these red checks here, are marked, we know an x has happened here. Similarly, if 2 blue checks are marked, we know there's a z error. And if we see a mixture of red and blue checks, it's either multiple x and z errors or perhaps a y error. So there are many ways to get these codes from symmetries, and I also think it's useful to think about kind of physics-inspired codes, so say codes from spin models. So you can think of the classical repetition code, which is the same as majority voting, as being an example of a 1D Ising model. So 1D Ising model has no thermodynamic limit, but we're not talking about thermodynamics, we're talking about kinetics. So I can look at the broken Ising bonds, and if I can fix them faster than they break, I can keep in either the all zero state or all one state. So codes we've been looking at a lot lately come from this compass model of x and z type interactions. And we call these codes compass codes. The original idea, which led to Bacon Shore, was from Dave Bacon. The Shore code and the surface code were not developed from this idea of a compass spin model, but we can map to all of these things. And we were able to show there's actually a wide number of codes in between. And these wide number of codes allow you to make codes which are tailored to the specific errors that are in your model. So if your errors are more inhomogeneous or they have a bias, we can fix these things. Okay. So then I want to talk a little bit about fault tolerance. So the first thing is this is, not everyone agrees with me on the following, but I think the following is true, is that fault tolerance is a design principle. It is not a physically measurable quantity. So when we design a fault-tolerant bridge or any internet structure, we say, okay, we're going to have so many cables break, whatever, but as long as less than 5 cables break, the whole system will work perfectly. So it's the same thing with quantum fault tolerance. We basically say we have a whole bunch of gates. As long as less than 5 gates break, things will work perfectly. So then we have to think about, well, what does breaking mean? So the typical choice are these Pauli errors. And then we have to build a decoder that looks at those breaking things. One challenge of fault tolerance is it naturally limits operations because we no longer have a continuous set. We have finite symmetries, which prevents us from having continuous control. And then if, when I do all this stuff, my errors improve, that means you're below threshold. All right, so again, I thought Professor Fuji had a very nice picture showing all the different types of errors, but I want to talk a little bit about the kind of challenges of designing fault-tolerant circuits. So in this plot on the left are two equivalent circuits for the blue 11, this blue 11 symmetry operator. And for those of you who know quantum mechanics, all of those control knots commute with each other, so the order should not matter. But if we do it in a fault-tolerant way, the order suddenly matters because this error, this x that exists in the middle, doesn't commute with those control knots. And as a result, this was first noticed by Yu Tomita, who was my student, who was interning at Microsoft with Christos Savore, that basically the errors will propagate into different ways. And when they propagate through, the next round of error correction will see very different syndromes. And now, if we do a minimum weight choice to fix it, on the top, we get back to no error. And on the bottom, we've created a logical X. And this is really, this temporal ordering to be able to achieve fault tolerance is a real challenge to expanding the number of codes that we can decode efficiently fault tolerantly. So in this particular case, what we saw was that these decoders actually can be related to the underlying compass model. And we can just use the compass model to decide how we organize these circuits. We were able to do that for a wide variety of compass models, basically all compass models, show that it's fault tolerant in all these cases. And my student, Shilin Wang, because it was a huge number of codes, he actually invented an improvement of the union find decoder that uses weights. So I heard there was this talk about putting the union find decoder into the cryo. Also, it's worthwhile to think about what is the extra digital logic to make it weighted union find. So what I'm really excited about is all these compass code work has been going on. I worked with Norbert Linke's group on kind of an emulation of larger Shor codes. You can think of this heavy hex code from IBM as an example of a compass code. And of course, the rotated surface code is also a compass code. And as mentioned before, there's been a lot of great work. So in our own work, we've been working on these ion chain quantum computers. We work very closely with Chris Monroe and Jung-San Kim. In the logic collaboration by ARPA, we are one of 4 teams built to make small logical qubits. We use Raman lasers to control the spin, the ground state spins of our ions. We put them into these surface electrode traps, which we get from Sandia National Labs. We also have an NSF-funded project to use these machines and build new machines for kind of near-term experiments called STACK. And then it's very similar to Sandia National Labs. The Department of Energy has a program called QScout, which actually allows for users to propose ideas. So if you have an idea for a small ion trap quantum computer, anyone from around the world can actually apply. Okay, so this is a picture of the system in Chris's lab. They can go up to chains of 28 171 ytterbium ions. The key thing is we have, everyone has a wiring problem, so we have 32 inputs through these optical fibers, 32 outputs through this 32-channel PMT. This data, it's like one of, say, the few silver linings of COVID, was taken when everyone was at home. So the lab was very stable, the air conditioning was very good. And these are the students from Chris's lab who worked on this. And I'll just note that Marco Cetina, who was a research scientist at the time, and Crystal Knoll, who was a postdoc, are now also faculty members with us at Duke. So here's the basic idea of the experiment. We have a chain of 15 ions. We use 2 of the ions to do nothing. They just help make the potential nice. We use 9 of the ions to serve as the data qubits. And then we have 4 of these syndrome qubits. Now, what's nice about this procedure is because in an ion trap quantum computer, you can do interaction between any ions in the chain, we don't actually have to make this geometry. It looks linear, but you want to think of it as a fully connected graph. So then we were able to measure these syndromes and then do some logical operations. So so this is all the things you'd like to do. You'd like to do logical gates, you'd like to encode, you'd like to do stabilizer measurements, you'd like to do error detection, and then you would like to actually do conditional rounds of error correction with mid-circuit measurement. So we were able to do all these pieces except for this conditional error correction. We'll talk a little bit more about that in a bit. So there's different ways to prepare these logical qubit states. So the Bacon Shor code has a very special property that it allows for fault-tolerant unitary prep. And again, to me, this is an example of kind of limits of our theories of fault tolerance, because normally you would say that's not possible. I have to have some sort of post-selection or detection to do the initial state prep. But in this case, just because of its structure, we basically make these 3 GHZ states. Now, those only generate 4 states on the Bloch sphere, 0, 1, plus, and minus. And if we want to do the other states, then we need these 2 more controlled knots and this arbitrary seed state. So I want to say that all of these fault-tolerant experiments people have done usually win on one element and lose on some other element. So the element we really win on is our spam, and that we're able to go to fault-tolerant, by using the fault-tolerant circuit to only encode 0 and plus and minus. When we do correction based on the output of the circuit, we're able to drastically reduce the error. And if we actually throw away all bad circuits, we never saw a bad circuit. It is really important in order to do universal quantum computation to be prepare these other states. So in this case, the direct preparation, again, we just start with some random state, and then we apply these control knots. We can do a fault-tolerant rotation between 0 and 1 and plus and minus because of the symmetries of the code. And then we can also, we can do any arbitrary unitary. So we can just do the arbitrary unitary, which is a continuous rotation on the whole code space. And so what we saw was that the direct preparation was actually quite good. And if we just kind of fit it to like a Rabi oscillation, we get very high amplitude, very little decay with correction, and just nothing with detection. With the continuous case, we see that we suffer. It's not fault tolerant, so we suffer from these weight 2 errors quickly becoming logical errors. And we estimate that our magic state preparation is about 2%. And I just want to point out again to Professor Fuji's talk, is that all of these red dots in between here are examples of those states you could use in this kind of in-between state between full fault tolerance and partial fault tolerance. Okay, we measured these stabilizer checks. Stabilizer checks, basically, here we're introducing error. So if there's no error, these should all be 0. If there's this Z4 error, right, this one should be 1 and the other should be 0. And what we see is that based on this dividing line, we get what you'd expect. We get what you expect. And then I also want to just applaud, applaud everyone working towards error correction, which is if this was I don't know, a simulation of something, I could mitigate these to 1 and 0 instantly, for free, basically. But in this case, I can't, because I, doing error correction, have to make decisions based on 1 bit, or in this case, 4 bits. So I get these 4 bits, I have to make a decision. Technically, in this case, we usually get 4 or 8 bits to make a decision. But that's a very challenging part, and that's why we need ability to do this decoding in space. Okay, so now, like I mentioned before, not everyone agrees with me about the definition of fault tolerance, and so one of the referees didn't agree with me and said that we'd not shown how to make fault-tolerant stabilizer measurements. That's fine. So I asked the Laird, Egan, to put an error into the middle of the circuit, and then we do the one fault-tolerant circuit, and we do the other circuit. And what he found is if he didn't put in any error, there's no difference. And I think this is really nice because our fault-tolerant errors are related to this idea that we could have any Pauli error at any point. But in this particular system, we basically have no Z errors. And because we have no Z errors, we actually don't have to bother worrying about it when we make this construction, which is kind of weird. So, but what's nice here is I add more error, here parameterized by this angle theta. What you see is that after correction, the fault-tolerant procedure does what it should do, and basically very stably returns a value close to 1. And then a non-fault tolerant procedure, will fail with 100% probability at the limit of there's always a z error here, because it cannot fix one z error. This one can fix one z error, but there are other errors in the system which limit this. So this is like the first example of how the how physical errors can really change how fault tolerance works. So this is a next example looking at the same, basic space. So when you're doing fault tolerance, you're always thinking about these stabilizer codes, stabilizer states, and the symmetries, and you rarely write down the state. But when you write down the state for this short code, you see that it's 3 copies of GHZ states, which we know. And we know that these GHZ states are actually great quantum sensors and maximally sensitive to magnetic field noise. So just by switching these stabilizers to be antiferromagnetic, we're able to basically massively increase the lifetime of our logical qubit, just by choosing a slightly different basis of the stabilizers. There's also been some nice work from my colleague Robert Calderbank, where if you can actually make this totally symmetric and you're guaranteed the errors are correlated, you can then make the error completely go away. So in this case, the errors do not completely go away because because the correlation's not, well, because there's only 3 qubits per row. Okay. So I want to touch again on this question of decoders. So in this 2 qubit per qubit thing where you can actually see a single point can be really helpful in improving the threshold, but also reducing the error probability. So in this work by Shruti Puri and Jeff Thompson, which was also part of our robust quantum simulation effort, they proposed a method to measure basically erasure in this Rydberg atom. So the qubit is here in this triplet P0 metastable state. The gates require using this Rydberg state. And then it turns out the dominant error sends it to states which are detectable, particularly here the ground state. So if it falls to the ground state, we can just detect by fluorescence. And so what Shruti was able to show in her calculations is that it shifts the threshold significantly, and also, importantly, it reduces how quickly the errors drop, because it also changes the effective distance, because the erasure errors can work on a much larger distances. And then I learned last week that Jeff now has an experimental paper showing this the ability to measure these erasure errors. So we were very motivated by that, and so my student Mingyu likes to call it erasure conversion trilogy. So we basically saw if we could do the same thing in trapped ions. It is a little bit different, and like where it pays off and where it doesn't pay off is tough. Kind of the most frustrating thing for me is that there's not enough known about ytterbium spectrum for us to decide if it will help in ytterbium or not. We need decay, for the specialists, we need decay rates from these bracket states and this sort of thing. But it looks pretty good, and our paper just came out at PRX Quantum. So I think this leads to kind of, again, in this idea that Hilbert space is vast. Here in this paper from Amazon, the idea is you just try to make a superconducting qubit where the dominant error is erasure. So you say, okay, I'm going to suffer from T1. That's going to be tough. But I'm going to make it so that T1 is always an erasure as much as possible. And that makes it a vastly better qubit for error correction, even if T1 is worse. And I think that's an interesting direction to head for other man-made qubits. So then I just want to say a few more words about this quantum error correction beyond poly errors. So these coherent errors, what's interesting is we've seen that people were really worried that coherent errors would add up too quickly and cause a lot of trouble. We saw before with a long time ago that basically it's not a problem for larger codes. As the distance increases, these coherent errors also decrease. What I think is more exciting is that you can actually, if you're given a guarantee that the error is mostly coherent, you can do some pretty fun things. So in this example, the error channel after every gate is the gate angle is slightly off. And so that angle slightly off is either coherently slightly off or it's been mixed, so it's kind of incoherent. And so a unitarity of 1, it's perfectly coherent. And at unitarity of 0, it's just random polynoise. And just by changing the way we put together our error correction circuit in this simulation paper, we can basically make the error go very, very small when it's coherent versus the naive way to do it. And this blue method of doing it is actually the way we did it in the experiment with Chris. Yeah, so we talked about these leakage errors. We haven't talked about leakage errors. So leakage errors is the opposite of erasure, or not the opposite, related to erasure. So you fall out of the qubit space, which is bad. Again, Hilbert space is vast. There's always somewhere to go. But you don't know. And so leakage can be a real problem, and you need some way to basically connect between these various, right? You basically need some way to detect it or refresh these qubits. So you can do it either by moving these qubits across each other, or by thinking of neat contraptions that take care of this leakage gadget. So the best thing you could do is if you could turn your leakage into this erasure. So basically, I like to think there's just a bell which tells you that you've left the qubit space, and when the bell rings, you can do something much better. Okay, so I think the reason why I titled the talk Quantum Error Correction Now is because the last 3 years to me have been a real explosion and blossoming of both experimental platforms becoming capable, but also kind of amazing advances in theory. So I spoke a lot about my theory, which is related to this tailoring to physical errors, and also implementing it in small quantum computers. But kind of perhaps more important is this idea of now having low overhead constructive codes. So Professor Kwashi mentioned that using these concatenated codes, you can make very compact error-corrected quantum computers. There's been a lot of work in these LDPC codes, which were previously proposed, but actually not, before were not constructive. There's a proof it exists, but not a way to actually build it. And then this paper, which is not quite an LDPC code because it's not quite linear rate. What it shows is with this thin, they call it thin planar connectivity. It's from Microsoft. In this thin planar connectivity, they're able to go from 1,000 qubits from their surface code estimate per logical qubit to just 50 qubits per logical qubit. And what is the cost? The cost is this increased connectivity between the qubits, and then also this, being able to go between these layers. So I think this is really quite exciting. And then I'll also note the theory of fault tolerance is transforming as people think about things like flow K codes and non-foliated cluster states. And I think there's actually quite a bit of opportunity there. All right, so all this work I talked about, almost everybody has left. Mingyu is still in the group. Natalie went to Quantinuum and was one of the key authors on this logical qubit gate using the Quantinuum ion trap. Mike and Dripto both went to Google, and they were, out of the 100 authors on that paper, they were 2 of the 4 authors that talked about the Google Symposium about how to implement the distance 5 code. Mian went to IBM. He's on the heavy hex code paper. Shilin just started a postdoc at Yale with Shruti Puri. And Narayanan, who is Robert Calderbank's student, is now a professor at the University of Arizona. And then Catherine, who is an undergrad, has switched to neuroscience. It's okay. Yeah, and then on the erasure errors, so Mingyu and I worked with Wes Campbell at UCLA. We're, of course, very grateful for the funding the US government has given us to do these experiments. And then I'll just, as an open invitation, if you find yourself in North Carolina, please come visit us at the Duke Quantum Center. We're growing quickly. We have a number of faculty in both theory and experiment doing different things. Thank you.